So let's start the last lecture of mine. So today I'm going to talk about how to determine the S matrix, in particular the spin chain S matrix, which describe n equals 4 super mu theory at finite coupling. So let me first start with a review. So yesterday we talked about how the spin chain arises from perturbation theory of n equals 4 super mu theory at weak coupling. And in the end, we arrived at some Hamiltonian, and I explained that the Hamiltonian can be diagonalized by making some ansatz to the wave function. And in particular, for the two Magnon states, the wave function had this form. So it's essentially given by a sum of plane waves, and importantly, these momenta, P1 and P2, were constrained by what's called beta equation, J not equal K, and S Pk, Pj equals 1. So this was the beta equation, which constrained the momenta of the particle, and it came from the periodicity condition. And this spin chain I talked about yesterday can be completely solved by these two sets of equations. So first you need to determine the momenta of the particles by solving this equation, the beta equation. And then once you determine the beta equation, the total energy is just given by sum of individual energies. So that was the story yesterday. And the punchline of my talk today is to, okay, so once you assume the integrability, then this kind of structure also persists at finite coupling. But of course, in order to be able to write down these kinds of equations, you need to know the ingredients. For example, this S matrix and this E to I pk, and also the energy. And the goal of my talk today is to explain how to determine these three quantities at finite coupling of n equals 4 super mu theory using some various observation and analysis. And the first thing I should mention is that, of course, yesterday the way we arrived at this expression is to really do the honest Feynman diagram computation and compute the Hamiltonian of the spin chain. Of course, you could also try to do it at two loops. But of course, if you go to higher loops, then it becomes very hard. Simply because doing the Feynman diagrams for at higher loops is hard. So higher loops is very hard. So, and in order to overcome this difficulty, that today I'm going to utilize symmetry and also a little bit of integrability. But let's first start by talking about the symmetry. So let's start talking about the symmetry. Oops. So the section 1 is symmetry. So the idea is to use the symmetry in a nice way so that you can actually fix the finite coupling S matrix and this dispersion relation. But before analyzing a real problem, let us recall one of the textbook examples of how the symmetry was used for, so which is classification of particles using Poincare groups. So this is, of course, a textbook example, and which you can find in many textbooks of quantum field theory. So, but let us briefly recall what we did in this case. So what we want to do is to classify the particles moving in Minkowski space, let's say with momentum k. And typical way of classifying the particle is to first go to the rest frame, in which the form momentum takes this value. And after going to the rest frame, what you are going to do is to ask what is the little group of this momentum. By little group, I mean like it's the subgroup of Poincare groups, which leaves this momentum invariant. And once you identify the little group, then you can classify some internal motion, something like an internal motion, like spin, using that little group. So let's explicitly write it down, what I said now. So step 1 is to go to the rest frame. And step 2 is to ask what the little group is. And step 3 is to classify the internal motion. Of course, well, this strategy is also used for not just this problem, but also for other problems. And indeed, that's essentially the same thing as the little group also appeared in previous lectures, in other lectures in this school. For example, in the lecture by Peter, he talked about stabilizer group, stabilizer of the configuration of 2- and 3-point function. And what I'm going to do is essentially the same as what he talked about, but now in the supersymmetric context. Okay, so let's try to do it. So let's try to follow these steps in the case of n equals 4 2-point function of n equals 4 super mu theory. So 2-point function in n equals 4 super mu's. And so let's first ask, what is the rest frame? Of course, you can choose arbitrary rest frame you like, but depending on the rest frame you choose, the analysis might be a little bit complicated. And I would claim in the case of 2-point function, the nice rest frame is given by this 2-point function of BPS operators. Okay, I'm going to explain what I mean by BPS operator, but essentially, I'm going to consider this configuration. And as I mentioned yesterday, this operator is protected by the supersymmetry and called BPS operators, half BPS operators. And in particular, this operator has, the dimension of this operator is exactly given by this power L. And this power L also, of course, determines the R charge of this operator, because each Z has 1 unit of R charge. So this is our rest frame. So then the step 2 is to ask what the little group is, or the stabilizer of this configuration. So let's first talk about space-time part, the conformal group part of the stabilizer, which is actually already discussed in Peter's lecture. So we are putting up operator 1 at origin and the operator 2 at the infinity. So the part of the symmetry group, part of the conformal group which preserved this configuration is clearly SO4, which is the rotation around 0 and infinity. So this is the space-time part of the little group. And in addition to that, I'm going to recall you that Z is essentially given by the complex combination of the 2 real scalar But we know that in n equals 4 super mu theory, there are actually 6 scalar. So in this configuration, I'm using 2 of 6 scalars. But there is still a degrees of freedom, which basically rotates the remaining 4. So in this way, you can also conclude that the symmetry coming from the R symmetry part, the global symmetry part, is also SO4. By the way, so this SO4 is essentially the same as SU2 times SU2. Well, in my talk, I'm not going to distinguish, for example, SO3, difference between SO3 or SU2, because that's not going to be very important. So these are basically bosonic little groups. And there are also fermionic little groups. So I don't have time to explain why they preserve the particular fermionic little group, but I'm just going to state, in addition to this, there are 8 supercharges, plus 8 superconformal charges, which preserve this configuration. So which in the rest of my talk, which I denote by Q's and S's. And a nice fact about all these little groups is that you can actually combine them into a nice supergroup, which is PSU2/2 times PSU2/2. So each PSU2/2 contains SU2 piece, SU2 times SU2 bosonic subgroup. And essentially, so one of the SU2 for each piece is coming from the space-time SU2, whereas the other SU2 is coming from the R symmetry SU2. Okay, so this is a general structure. And in addition, furthermore, in addition to these, there is yet another charge which preserves this configuration, which is D minus J, where D is the dilatation operator and J is the one of the R charge. And it is clear that this also preserves this configuration because, as I said, this operator satisfies this equation. Both delta and J are given by L. So J is, so J is the R charge which rotates this complex scalar, Z going to e to alpha times Z. Sorry, each of
8 U's and 8 S's, these are all Weyl spinors, right?
Yeah, the spinners. They are spinners. So, okay, so let's see. Right. So now, and the point is that this D minus J turned out to commute with both PSU2/2. And so this is actually a central charge. For this PSU2/2 square. So this is everything that you can conclude just by looking at the global symmetry of the problem. And so this is the end of that step 2. And now I'm going to move to the step 3, which is to use this symmetry group to classify the internal motion. So step 3 is to classify the internal motion. So in order to classify the internal motion, you first need to ask what are the internal motions in this case. But essentially, what I mean by internal motion is basically like inserting some other fields inside the trace. So by inserting some other fields inside the trace, originally the configuration that I was talking about only contains z. But if you want to describe more like a most generic operators, of course, you need to insert some other fields inside the trace. For example, maybe it might be some fermions, or it might be some other complex scalars, or it might be some derivatives, covariant derivatives. So X is basically other complex scalars. And the question is whether these insertions can be classified using the symmetry group that I just described. And the answer is yes. And it turns out each insertion can be regarded as bifundamental of the PSU2/2 squared that I just described over there. And so let's see. So this is insertion. And because it is bifundamental, so it has two indices. So one index is PSU2/, the index for PSU2/2 left, and the other index is for PSU2/2 right, where left and right are just like two groups which appear over there. And in the rest of my talk, because it has the bifundamental structure, I'm going to express it something like in this way, because sometimes it's useful to just talk about one index. Well, it's simpler to just talk about one index. So in the rest of my talk, I'm going to denote this Magnon insertion in this way. Okay. And let me be a bit more precise by what I mean by this notation. So each index A and A dot are fundamental representation of PSU2/2. And because it's supergroup, it's useful to consider two index as bosonic index. So that's why I use phi. And the rest of the rest indices as fermionic indices. And same for chi A dot. And in this notation, let me write down what each field corresponds to in this notation. So first of all, you can, for example, take a combination of like a phi1 dot, which like both of which are bosonic indices, and that corresponds to some scalars. For example, some other complex scalars x. And instead, if you take phi1, phi2 dot, you get y. So these are basically the relation between the n equals 4 fields and this notation. And on the other hand, you can also choose two fermionic indices, psi alpha and psi alpha dot. Then that gives you the covariant derivative. So essentially, this alpha and alpha dot are basically spinor indices. And you can also consider a bit more complicated one, like a one fermionic index and one bosonic index. And of course, as you can imagine, they basically correspond to fermions. Sure.
The dilatation operator naively preserves 0 and infinity.
Yes.
The dilatation alone is, or the C minus J is also preserved J alone.
Right. That's okay. So here, it's true that if you act dilatation on this configuration, of course, dilatation picks up some factor from like the operator at the origin, but you get the compensating factor at the operator from infinity. But here I'm talking about some generator which really preserve each operator separately.
So you wouldn't be able to see it from this.
Right, right. Yeah. Well, take this configuration and ask like what are the generators which preserve each configuration, each of two operators separately. Okay. Right, so nice. So this is essentially how the symmetry. All right. Okay. So how the symmetry constrain. Well, what is the symmetry little group and how the symmetry acts on the internal motion. So once we understood what is the symmetry and how it acts on this like Magnon excitations, then you can try to use PSU 2/2 squared to constrain dynamics of magnons. However, it turns out this is not very powerful. So one big problem is if you just use this symmetry, there is no way to know coupling constant dependence. Well, this is also actually a common problem also in Bootstrap. For example, if you consider some supersymmetric series, supersymmetric CFT, which have some exactly marginal directions, then typically just considering the symmetry is not enough because you can never like specify one series because there is a line of fixed points. So in that case, typically you need some additional input which allows you to know about the coupling constant dependence. So also here that is the problem because I just talked about the global symmetry which doesn't know anything about coupling constant dependence. So the next question will be how to understand or how to incorporate the coupling constant dependence. And that's going to be the next topic. And the punchline is that we can use some gauge symmetry. I call it large gauge symmetry to incorporate the coupling constant dependence. I'm going to explain what I mean by this soon. So the key idea to overcome this problem is to, so far I've been talking about the single trace operator of finite size, but the key idea is to consider infinitely long string of these and effectively forget about the trace. Of course, it's probably not clear why this is a very useful way to think about the problem, but let me explain two advantages of doing this kind of stuff. So advantage one. So advantage one is more or less obvious. So originally, you had some like a theory on a cylinder. It was theory on a periodic spacetime. For example, if you map the problem to the spin chain, you get like a periodic finite size spin chain. And on this periodic finite size spin chain, if you go to higher loop, Magnon interacts in a very complicated way. And it's a little bit hard to try to keep track of the detailed dynamics. and try to write down the Hamiltonian explicitly. But one advantage of considering like an infinitely long chain is that now you can just study the problem just using the S matrix. So the big advantage is that once you go to the S matrix description, you don't really need to talk about the intermediate complicated dynamics. You just need to ask what happens if you insert some particle and measure some particles at future infinity. So this is technically very nice because it allows you to incorporate the symmetry in a simple way.
Sorry.
Yes?
What happens to the periodicity condition?
Sorry?
What happens to the periodicity condition?
Okay, yeah. At the end, of course, we do need to impose the periodicity condition. And that is essentially the beta equation. But the goal of my lecture today is to describe, to determine all the ingredients which appear in the beta equation. And for that purpose, it's actually much better to consider like a infinitely long chain.
Don't worry that I'm inserting more than 10 operator insertions and I'm doing the one over.
Okay. You can, okay.
There's some Canadian limits maybe.
Yeah, n is always much larger. So it's a little bit like tricky to like exactly say what I'm doing. But so I'm taking L to be very large, but much smaller than n. Because if L is of order n, then there is no distinction between single trace and double trace, and the things gets more complicated. So this is the basic idea. And the second advantage, which is more important for us, is the following. So the second advantage is that if you consider infinitely long chain, then some of the gauge symmetry which was acting on the cylinder becomes part of this global symmetry. So in particular, some of the gauge symmetry which don't die off at infinity, you should treat it as the global symmetry. And this is what I'm going to talk about next.
When you say infinite C's, they're all at the same point, right?
Yes, all at the same points, yes.
How does large gauge symmetry become?
Yeah, I'm going to explain that. Yeah, so it's not the large gauge symmetry in the usual sense. That's why I put quotation mark. But there is some notion of large gauge symmetry, which I'm going to explain now. Okay, to understand what I'm talking about, let's recall the SUSY transformation. And let's recall how it acts on fundamental fields. So we know that if you act SUSY to boson, we get fermion. So maybe you get something like this. Yeah, I don't really care about indices. So this is some gamma functions. Sorry, the gamma matrix. And if you act SUSY to fermions, then you typically get a bunch of terms. But what's important for me is this term, which is I over 2 times coupling constant times some commutator of bosonic fields. So this exists in SUSY transformation rule of n equals 4 super mu theory. And one simple consequence of this SUSY transformation rule is that if you act the SUSY twice to the to the fermionic operator, to the fermionic field, then you get, it contains some term which looks like this. Well, where phi is some bosonic field. And so this is basically field-dependent gauge transformation. And I should point out, because this is, just because this is gauge symmetry, it knows about the coupling constant. Okay, so this is a kind of generic symmetry transformation structure. And in particular, if you consider supercharge, which is inside PSU 2/2 squared that I was talking about. Yes?
When you do two gauge transformation, two gauge transformation, the epsilon parameter.
Yeah, okay, so actually, yeah, you need to, so this delta, so this is very schematic, so you actually need to act the SUSY generate, two different SUSY generator. So that's what I mean by delta square. Yeah, so you need to take appropriate one, because if you take the same one, then you just get 0. So roughly, so this is just pictorial explanation. And in particular, if you take some SUSY generator in PSU 2/2 and act it twice, again, this square is not the square of the same thing, then what you get is this one. So this scalar field actually is, in this case, the Z field, which I used to make a long chain. And let's denote this right-hand side by as the action of some operator on the magnum. Of course, this is just a gauge transformation, as I was talking about. And let's consider what happens if I act this generator P hat. So first of all, if you act the generator P hat to single trace operator, then what you get is the trace of some commutator, which is, of course, 0. This is, of course, good, because I was saying that this is just a gauge transformation. So if you act the gauge transformation to gauge invariant object, you should get 0. And you should explicitly confirm that. But something interesting happens if you open up the trace and consider infinitely long chain. So that's what I'm going to talk about next. So to see the consequence of that, let's consider the action of P on this something like one magnum state, e to the IPN plane wave state, times that z. So you have a string of z's, and then you have m's at n's position. Let's try to see what happens. So P is basically the commutator. So you can simply act it. Then the result is given by sum of two terms. And in the first term, you insert z in front of m. Then originally m was at n's position, but now n is now n plus 1's position. And then you have minus mz, But in this second term, m is still at n's position. You can further rewrite it in this way. Okay, so I was forgetting about g, which is very important, which is the coupling constant. So you can further rewrite it in this way. Just shifting n in the first term. Now, this basically is the same state as the original state. Of course, there is some small subtlety because I inserted extra z. Actually, the length of this string becomes a little bit longer. But because I was thinking about like infinitely long chain from the beginning, you can basically neglect the difference. So this basically tells you the action of this P field, P generator on this like a plane wave state. But if you look at this action, then you can immediately see like some nice feature. So this kind of eigenvalue is also given by the action of the translation generator on the spin chain. So this means that this P, which was originally just a gauge transformation, can now be interpreted as a translation on the spin chain. And furthermore, I should emphasize that the action of P on this infinitely long chain is non-trivial, unlike the action of P on this gauge invariant operator. So this is very important, and right. So this is very important because it's telling us that the generator P, which was originally given by some like a square of Q, now knows about some dynamics of the spin chain. And in addition to this P, there is yet another generator I need to talk about. But this generator I cannot actually explain in this lecture. So I just claim that if you do the two-loop analysis, you also find that instead of P square, you now consider S square, where S is the superconformal generator. And if you do the two-loop analysis, you conclude that S square acting on M now gives you something similar, but now with Z inverse. So this actually like reduces the size of the spin chain. And I'm going to denote it as K acting on M. So in total, the symmetry, original symmetry of PSU2/2 plus D minus J is enhanced to this symmetry because we acquired 2 extra generators. And this turns out to be a very powerful symmetry group which constrains the dynamics of the spin chain. And I should also say that I already said that this is the central charge, but it turns out that this and this also commutes with other generators, so they are also central charges. Well, the reason why they commute is basically because they came from gauge transformation. So it shouldn't affect other space-time symmetry.
Do you commute with each other?
Sorry, yeah, commute with each other as well. So now I'm going to talk about the centrally. So I'm going to talk a little bit about the structure of this algebra, which is first proposed by Weiser. And so, but before doing that, let me just remind you that, okay, let me explain my notation about the generators in PSU2/2 squared. Because it has the product structure, I'm going to focus on just one of them. And PSU2/2 contains Q. Okay, I forgot the notation actually. Q of, let's see. PSU2/2 contains Q of alpha. Okay, so let's first go to the next section. Centrally extended PSU2/2 square And PSU2/2 square. So original PSU2/2 square contains, so supersymmetry generator and superconformal generator, and the R symmetry generator and Lorentz generator. So this is R symmetry, and this is Lorentz. Okay. And as I was saying, if you take the square of Q or square of S, you will discover some central charges. And because I thought I don't have time, so I just wrote it down here. So, but you don't really need to kind of write it down. I think if you want to write down something, then you can just, well, you can just write like a QQ equals P hat or this kind of general structure, because the indices are not so much important for the rest of my lecture. So this is essentially more precise statement of what I was saying. So if you take the anticommutator of P, then you discover the gauge generator P hat. And if you take the anticommutator of S, you discover the gauge generator K hat. And if you take the anticommutator on Q and S, then you generate Lorentz and R symmetry. And in addition, you get C hat, which in my notation is D minus J over 2. Okay, so then once you understand the algebra, now you also need to know how it acts on the spin chain excitation. So this is how it acts on the spin chain excitation. Well, the general structure can be inferred just from the transformation rules in N equals 4 super mu theory. So this is essentially just telling us that Q acting on boson converts it into fermion, and Q acting on fermion converts it into boson. And so, and the same is true for S and S. And if you want to be a little bit more precise, then there is actually a factor of Z here and factor of Z inverse here. And this is essentially because as I was saying over here, so this is, the fermion, the SUSY transformation of the fermion gives you some boson, but not just boson, but it's the commutator of boson. And if you are careful, then you discover that you should insert some extra field here, which is Z here. And these A, B, C, D are so far just arbitrary. And I'm going to explain a little bit how to understand how to determine those values of A, B, and C, D. But before doing that, let me just say that by taking this action and using this, okay, maybe I shouldn't erase this one. So using that commutation relation, you can also compute the action of CP and K, and C acting on something chi is essentially given by 1/2 AD plus BC, AD plus BC, sorry. Whereas P acting on chi is AB times Z times chi, and K acting on chi is CD times Z inverse chi. Okay, so this basically follows from this blackboard and that blackboard. So now let me talk about a little bit about what are these ABCD are. And actually, ABCDs can also be determined by the consistency conditions. So what are the consistency conditions? So firstly, you need to impose that this ABCD correctly kind of reproduce the structure of the algebra. So in particular, you need to require the closure of the algebra. In particular, well, this is essentially saying, I'm basically saying that you need to require that this is actually the correct representation of the full PSU2/2, because here I only specified the action of Q and S, but you need to make sure that this is really consistent. And from that consistency condition, you can actually show that AD minus BC must be 1. And in addition, you want, if you impose the unitarity of the representation, there is yet another condition. So let me now count how many parameters do we have. So I originally introduced 4 unfixed parameters, and now I impose 2 conditions. So there are actually 2 parameters left. And this is actually good because 2 parameters basically have physical interpretation. So one is coupling constant dependence, because as I was saying, that this algebra should know about the coupling constant. And 2 is momentum dependence, because we expect each Magnon excitation to carry some definite momentum. So it is natural that there are actually 2 unfixed degrees of freedom. But of course, it's good that counting works, but it's much nicer if we can kind of parameterize ABCD in a way that physics is more manifest. And there is indeed such parameterization, and that's what I'm going to write down now. And the parameterization which makes physics manifest is as follows. So let me just first write down the parameterization and explain what it means. So A, I'm going to parameterize in this way, and B, yeah, it's a bit boring to write it down, but it's a little bit important actually. And C is I square root G gamma over X plus, and D square root G X plus over I gamma times 1 minus X plus over X minus, and gamma is square root I X minus minus X plus. And okay, so G, so that now that I need to define what our X plus and X minuses are. So X plus and X minuses are defined in this way, and the function X is defined by this condition. Okay, so it's a little bit complicated, but well, you just need to check that actually there are 2 free parameters. And in the end, the free parameters are just U and G. And U basically parameterize the momentum, and G is the coupling constant. Okay, it's a bit vague, and maybe you don't understand why this describes physics. But in order to see why this describes physics, it's good to look at the action of P hat. So let's take the action of P hat. So the action of P hat I determined by the commutation relation to be A times P. And if you just multiply A times B, what you get is A times B is G times 1 minus X plus over X minus. And this is a little bit, okay, let's see if I still have that blackboard. Yeah, no. Okay, so this is a bit similar to what I argued previously. So I argued previously that, maybe I have that here. No, okay. So I argued previously that action of p hat is basically that translation. And it also comes with the factor g because it comes from the gauge transformation. And indeed, here you see the gauge transformation. And here you see some combination that looks like translation. If you interpret e to, so if you interpret this guy to be e to ip, so then this action looks like translation. And basically, this is telling us in this parameterization, I should interpret x plus over x minus as momentum. So this is what this formula is telling us. And now let me just erase this. And okay, so I can also, okay, so let's see. So let me write it down explicitly, the dispersion relation. So I was saying that this should be interpreted as e to ip, and this p should have interpretation of moment of magnum. And also, we know what the energy is just from this algebra. And the reason is because this E is, so energy of the spin chain in the previous lecture was related to the anomalous dimension. And this anomalous dimension is also related to the eigenvalue of the dilatation operator. And well, this J just subtracts the classical dimensions. So, and this D minus J, I actually defined it as 2 times C. And we also know the action of 2 times C, which is AD plus BC. And I can just compute AD plus BC using that parameterization. Then it basically gives you 1 plus 1 over x plus x minus over 1 minus 1 over x plus x minus. So this basically gives you the dispersion relation of the magnum. Okay, so this still might look a bit abstract because it involves a complicated function x over x. But let me just say that you can actually derive the relation between E and P by solving these two equations. And in the end, you get the relation like this. So so this is the same as E equals square root of 1 plus 16 g squared sine square p over 2. And this actually has several nice features. For example, firstly, when g is very small, namely if you're at weak coupling, you get 1 plus 16 g squared plus sine, maybe 8. 8 times g squared, the sine square p over 2. But this sine square is, of course, the same as 1 minus cosine p. And this is precisely the dispersion relation of the magnum that I derived yesterday. And secondly, if you take some nice limit, for example, when g is finite and p is small, then this gives you some relation like E1 plus something times p squared, because you can approximate sine p by p. So this also gives you, in certain limits, a relativistic dispersion relation. And in general, this dispersion relation basically interpolates the weak coupling spin chain-like dispersion relation or relativistic, like a sigma model-like dispersion relation. And this is, of course, very good for ADS-CFT because we believe that this system at weak coupling is described by the spin chain, whereas at strong coupling is described by some sigma model, which should have some relativistic dispersion relation. because it corresponds to the excitation on the string worldsheet. Okay. So, and let me further explore a little bit about this dispersion relation, because this will be used in Pedro's lecture about hexagons in the so let me discuss a little bit about the structure of this dispersion relation. So in order to do so, it's better to go to U parameterization. Okay, I just erased actually U parameterization, but let's consider the analytics, some analytic structure of this dispersion relation. So as I showed over there, they are given by x plus and x minus. And I said x, the function x, is given by this equation. But of course, you can also invert it and express x explicitly in terms of u. And if you do so, you get this equation. So basically, this equation is telling us x of u has cuts. And in particular, and because this EIP and energy, momentum energy, are given by x plus and x minus, it turns out momentum and energy has two cuts. One associated with x plus, and the other associated with x minus. And one interesting feature of this existence of branch cuts is if you start from somewhere here, and then if you cross, for example, cut of x minus, and comes back to the same place, then it turns out by going through the branch cut, you replace x plus minus to 1 over x plus minus. And then let's try to see what happens if I cross branch cuts of both branch cuts. And if I cross both branch cuts, both x plus and x minus becomes inverted. And firstly, it's easy to see what happens to momentum. So momentum was given by x plus over x minus. Then if you cross the cuts, then it becomes x minus over x plus, which means that you actually inverted the momentum. And actually, it is actually easy to see that the same is true for energy. So by going through two branch cuts, you basically invert momentum and energy. And what is this the physical interpretation of these two minus signs? And it turns out this is essentially the crossing transformation, or particle-antiparticle transformation, which takes a particle in the past and brings to the particle in the future. Is this point clear? So it turns out that this analytic continuation basically corresponds to the crossing transformation. And the structure of the crossing transformation is actually encoded in the existence of these branch cuts. And so this is a kind of interesting feature of this dispersion relation for n equals 4 super mu theory. And okay, so let me just comment that there is some indication that so the existence of this branch cut is kind of weird from the point of view of ordinary spin chain, because we don't know any other examples in which the dispersion relation contains branch cuts. But there is some indication that this branch cut comes from some condensation of eigenvalue. Okay, this is probably a bit mysterious comment, but condensation of eigenvalues. in large N matrix model, large N matrix. Okay, I made one exercise related to this point, but let me clarify a little bit more about what the comment. So in some cases, you can actually compute the same quantity using integrability and also from localization. And in that case, localization computation basically like reduces the computation of n equals 4 super mu theory to a certain large N matrix model if you want to study planar limit. And in that case, because you're in the large N limit, the matrix model eigenvalue condenses into a branch cut. And if you really compare the details of the computation of integrability side and the localization side, then you discover that the branch cut you discover here, you find here, actually corresponds to the branch cut of the eigenvalues of large N matrix model. So there is an indication that this branch cut is really coming from large N matrix model. So it seems this existence of branch cut is really important and really reflecting the fact that this integrable model is coming from some large N matrix field theory. Okay. So this was just a comment that I wanted to make. And now, okay, so let's see. I talked about the dispersion relation. So, yes. Yeah. So essentially, this integrability is telling us that, roughly speaking, magnon in the spin train just continuously becomes some excitation on the worldsheet. So although the dispersion is completely different, but this is kind of telling us that it's going to be some, well, it's just that the magnon becomes the excitation. But I should also point out that you only discover this dispersion relation in certain limit of the momentum at strong coupling. So even at strong coupling, for example, if you just take G to be very large, keeping P to be fixed, the dispersion relation that you find, again, is given by some sign. So there is some sign also in the, you can also find some sign at strong coupling. I can make more comments about this, but yeah, probably it's better to discuss after the lecture. So, okay, so far I've been talking about dispersion relation, and I explained that dispersion relation can be fixed by the structure of centrally extended PSU2/2 squared. But it turns out, okay, so then the next task is to determine yet another object, which is S matrix, because that's also important for us to write down the Bethe equation. So again, as in the previous lecture, well, as in the first lecture, I'm going to talk about 2 to 2 S matrix, assuming that multi-particle S matrix factorizes. And as I said, each particle carries 2 indices, one for each PSU2/2. So I have BB dot here, and CC dot here, and BD dot here. So this is the S matrix. And because of the symmetry, what we can first conclude is that this S matrix should factorize into 2 parts. Well, this is just a consequence of the fact that each magnon belongs to the bifundamental representation of PSU2/2 square. And there might be some overall scalar factor. And so let's denote this whole object by this, because it's important. And now what I'm going to do is very simple. Because we identify the symmetry of the system, I'm just going to impose that this S matrix must commute with G, where G is the element of the centrally extended PSU2/2 square. So this twiddle means central extension. So this is actually the same strategy as the one I took in the ON analysis of ON model S matrix. In that case, I first imposed the ON invariance, and then I discovered that then I argue that S matrix is basically should be given by a combination of 3 index structure, this and this and this. And there is also like a more representation theoretic understanding of why we have 3 structures here. And basically the reason why we had 3 structures in the case of ON is because if you take the tensor product of 2 vector representations of ON, then you can either get singlet or antisymmetric representation or symmetric representation. And for each representation, I can choose arbitrary coefficient. So that's why in the case of ON sigma model, I had 3 different structures. And what I'm imposing here is the same symmetry constraint. But if I impose this symmetry constraint for this centrally extended PSU2/2 squared, there is some surprise. And the surprise is that there is actually only one tensor structure allowed by the symmetry. And let me briefly explain why it is so. So this might be a comment for some expert. And the reason is because each magnon actually belongs to what's called Shota representation. So in conformal group, generically, there is, okay, so also the Shota representation also appears in the conformal group. And for example, if you consider the stress energy tensor or some conserved currents, then the size of the representation of those multiplet is much smaller than the generic representation. And also here, these magnons turn out to be what's called belong to what's called Shota representation. And generically, the condition, the short for a representation to belong to a Shota representation is this condition, where n is some integer. And it turns out that magnon that I was talking about is a very particular case where n is 0. And so this is actually the smallest Shota representation, which is 4-dimensional. So that was the representation I was talking about. And this CPK are eigenvalue of the central charges. And so what I wanted to do by doing this analysis is to ask what happens if you take a tensor product of this like a shortest Shota representation and try to decompose it into general representations. And so, okay, so let's call this F because it's the fundamental magnon. So what I want to do is to decompose tensor F into some representation. But now the fact that n equals this symmetry group has 3 different central charge plays a very important role. So if you take the tensor product of 2 representations, then basically the central charge adds up to C plus C prime and P plus P prime and K plus K prime, right? But what's important is that if this representation, even if this representation and this representation satisfies this shortening condition, generically, if you just sum these two, then the resulting vector doesn't satisfy shortening representation at all. So this means that the one which appears on the right-hand side is basically generic representation or long representation. And it turns out the only long representation which can appear is here. The minimal long representation which can appear on the right-hand side has dimension 16. This basically means, so we know that this F have four-dimensional representation, and this F is also four-dimensional representation. So this basically means that there is actually only one representation which appears in the tensor product of F and F. This basically means that there is only one tensor structure that you can write for this S matrix. And that's basically the reason why, why you can actually fix this tensor structure just by imposing this symmetry condition. So this S matrix part is completely determined. So I'm not going to write down the structure of the S matrix, but this is actually very important consequence of the analysis. But of course, and people actually wrote down, Nicholas Beizet wrote down this matrix, but it's actually a bit complicated. So it's again given by X pluses and X minuses, and I don't have time to write them down. So by doing this analysis, I said that you can basically fix just the S matrix. So what you are supposed to, so the only remaining part is this overall prefactor. So if you recall the first lecture about ON model, there was also some overall prefactor which was unfixed by the symmetry analysis. And we basically fixed it by imposing the cross-end symmetry. And the story is actually also true here. And basically, you can utilize this analytic continuation, which can be interpreted as a cross-end symmetry, and then impose the cross-end symmetry. And by solving the cross-end symmetry equation, you can determine this overall phase as well. Okay. So now let me end my lecture by mentioning a further surprise. So by doing this analysis, we can determine the structure of the S222 S matrix completely. But so far, I didn't use at all any integrability. I just used the symmetry and perhaps some large gauge symmetry to constrain the structure of the S matrix. But there is some further surprise. So the further surprise is as follows. So if you take this S matrix, then just compute this picture. So here I put some matrix here, and here I put some matrix here, and here I put some matrix here. And I also compute this picture. Then it turns out this actually satisfies the M-Baxter equation. Of course, this is not a proof of the integrability, but it actually strongly supports the conjecture that n equals 4 super mu theory is integrable at finite coupling. So now the strategy is to just assume that n equals 4 is integrable and it satisfies the M-Baxter equation. Then you can write down the beta equation. And furthermore, energy is given by, because we already fixed the dispersion relation, I can also compute this E of P, and you can compute the energy by summing up the constituent energies. And then this should be giving you the anomalous dimension of the operator. Yeah, there is also, of course, this is just the beginning of the story, how people solve the n equals 4 super mu theory. And there is also further story of like reformulating everything into a nicer framework, and also including some finite size correction, which I completely didn't talk about today. But I think this is essentially the essence of how people solve the n equals 4 system theory, and you will see that the same strategy will be also useful for understanding hexagons Pedro talked about yesterday. Thank you very much.